Let's go back to electronics and talk of India's semiconductor ambitions. You led the thought revolution to tell the governments of the time and the people largely also that we had missed a bus and that there was time, it's about time we realized how to not miss the future buses. Where do you see India's semiconductor ambitions today? I mean, the end to end value chain from IP creation to fabrication. And where do you see us 10 years from now?
Well, I don't think I'm needed to tell the government or anybody. I think everybody realizes that we missed many buses. It's not that it's not realized. In fact, this especially in semiconductors, this realization because we were actually not too far from being in the ground floor even as late as 1990. We actually had a semiconductor manufacturing capability in Bharat Electronics to make transistors, which was shut down. This was the first era,
Wow.
1960s, 70s, right? In fact, when I was a student, the transistors that we bought in the market to do our electronics lab were all Bharat Electronics transistors, not imported
In
transistors.
fact, as a little bit of an aside, there's a book that Chris has written, Chris Gopalakrishnan, in which he talks of India, Homi Bhabha, having led a team to build a supercomputer in India.
Maybe, yeah, I don't know about it, but yes. So I think that there was nothing in the world other than transistors in
Yeah.
1960s, and we were building them.
Yeah.
Then when the first chips came in the 70s, we had decided to quit that. But then we came back with the semiconductor complex in Chandigarh, and we had a pretty not too reasonably state of the art capability. We sort of let that slip in the 80s, and then we upgraded it even in the 90s to a state of the art capability with Tower Electronics as the technologies provider. Then there was a fire and we lost everything. And then somewhere they took a decision that, oh, we can't get into this. We should focus on our strength. There was this alternative theory in economics that you focus on your strength and so on. And we stopped. And when we stopped, that was Moore's law was in full play. Every 18 months, things were doubling in capability. And several exponents, doublings we missed. And the barrier to entry, I think by 2010, 12, even before that, maybe the country was clear that we can't afford not to be in this. There are too many vulnerabilities from a national security angle, from a trade angle, and so on. So we wanted to, but it became harder. And the reason it became very hard is you can sort of measure the level of difficulty in terms of simply this one parameter that people throw about even in the late literature, which is what the so-called feature size, nanometer. So the feature size is sort of the size at which you etch individual electronic components in the chip. So when we tried to come up to the state of the art in Chandigarh in the early 90s, the feature size had just come to below 1 micron. In fact, I remember when we were doing our wireless local loop system, 1 micron barrier was crossed and was announced in a big way, and 1,000 nanometer. Okay, and when Chandigarh was rebuilt, it was 180 nanometer, which was considered state of the art. And but to give you an idea, 180 nanometer products are still growing in volume. Many things can be built very well with 180 nanometer. You don't need lower feature sizes, so it's still growing. It's not a business that companies are willing to give up. Okay, so we actually had started with that at the right time, but we still didn't pursue it. Then it went to 90, then 45, then 28, and so on. And now it's down to 3 nanometer. Right. So every one of those halving, the barrier went up. Right, and the barrier went up because of two things. One is the machines that you need to do these become more and more expensive. So you have to run this factory more efficiently to recover the investment. And beyond, when it went below 28 nanometer, and particularly it went to 14 and below, even the nature of the technology machines changed. The technology, the physics, underlying physics, which was at play to do these things, what you do those machines itself changed. And even the getting the yields in the factory with those machines became also part of the IP. It's not just putting the machines, running it all as per the manuals, right? You had to actually learn things on the. So the barriers became harder, and the investments required to get such a factory going became higher. So the risk taking required became higher. So it became harder to get these investors who take the risk to set up these factories. So by the time we've actually come to the point now where we are setting up our first big fab in India with 45 nanometer feature size, which can be fairly straightforward way reduced to 28 or 22 nanometer. Then to go to 14 is another big step. is by the time we've done that, it's became almost, there's only one that's been set up now. Somebody has found it, and the government has had to subsidize it to more than 50-60% for somebody to take the risk. Okay. That's what has happened, and yet so that's really the danger in not getting in at the ground floor. Imagine, we are very strong even in IT services. To take an example where we are in the driving seat, IT services is a little bit like setting up semiconductor factories in the 90s. And why did the countries that make the machines allow others to set up the semiconductor factories? Because they felt that it's not a very important part of the value chain. And in fact, they are selling the machines upfront. They are recovering their investment upfront. Let somebody else, churn out the chips. Why should we do it? That's how it was done because the Americans are pretty much behind the technology for all this. So why did they do that? Because that's what they. Then when the technology started becoming better and better, then the actual running of those machines, the actual getting the yields became important. So some of the IP started residing in those companies, and that's now they're worried about that. They suddenly woken up to that, Americans and so on. But if you take you know countries like India, we are such a huge consumer, and there's a national security angle to this. The same technologies are vital for in defense and so on, or even denial can lead to a problem. So we want to have our own supply chains, and then we want to set up these factories. And now it's very hard to get the investors to take the risk. It's very hard to, because it has to be commercially viable. And then even if you do it, even we get to the point, let's say we do 14 nanometers and 7 nanometer, 3 nanometer. You remember that all these machines still all over the world come from a very few vendors, and they control the switch. So there is still a huge, of course, as I said, many of them have GCs in India and so on, but that's a different matter, question of who controls the switch. So this is a technology in which still I would say there are very, very huge barriers. But you have to have, you got to just like in electronics manufacturing, if you don't assemble phones, some people used to say, oh, what's the use? It's very low value add, it's women and men sitting at benches putting things together. But if you don't even do that, how can you hope to even replace some components in it? Yes. Right? If somebody else is doing it, why would he take your component? Right? So you've got to do everything. Right? Then only you can hope to, maybe at some stage we'll make a machine that does something better in that. But if you don't do it, if you don't run those machines, how are you going to even figure out what's a better machine?